Welcome students to the second lecture of logic and distributed control system. So last class what we have discussed that as an introductory that why or what are the things we are going to cover, what are the topics we are going to cover in this course, that is logic and distributed control system. Then we have discussed that one of the key factor which is very important for the revolution in the industry, that is automation. So we have defined the term called automation, and after that we have defined, or we have discussed how the automation will be achieved, and we have understood that automation will be achieved only by using feedback control system. And after that, very important thing we have discussed, that is called automation pyramid, because this automation pyramid will help us to understand that what are the responsibilities of different persons involved in the industry. So last class we have defined the automation pyramid having different level, that is level 0, level 1, level 2 and level 3 and level 4. And as we will move from level 0 to level 4, we have understood that how the responsibilities are going to be changed, the persons involved in each level. And also another important thing we have understood, that what are the uses of each and every level. And now, as we have discussed in the last class, that we want to understand that what are the uses of computer in control paradigm, because the automation came this automation came to the industry with the hand of use of computer as a controller. So we want to know that how the computer is going to play an important role to build the automation. So that's why the next topic what we are going to discuss, that is the uses of computer at different level. So to understand the uses of computer at different level of automation, we have to understand the hierarchical control. So in modern computer control system, several layers of control can be superimposed onto the basic controls which are physically connected to the process. Okay, so because we have understood that in level 0, in automation pyramid, in level 0 the sensors and actuators directly communicating with the process, and the information is passing through to the next level, level 1, where the basic controls are there. Okay, and each and every loop will be controlled by the basic controllers, and all the loops present in the industry, a specific industry or in the process industry, will be supervised by a control system called supervisory control system. Okay, such hierarchical control uses several levels of computer system in an extended master-slave relationship to carry out not only the process control but also the supervisory management and business function in controlling industrial plants. So from here it is very much clear that what are the uses of computer in the automation. They can be used as a simple process control, or they can be used as a supervisory management, or they can be used to execute the business functions. Okay, this sections describes the historical evolution of hierarchical control and some typical forms of such control systems, including the distribution of the potential duties among the several levels of computers involved. Okay, so the uses of computer will be understood if we will able to understand what are the hierarchy present in terms of control in industry. Okay, so one example has been given here. You see, as I told you that the modern control systems are well suited for hierarchical control, because level 1 controls, which consist of devices that devices with direct connection to the processes. Okay, so this is the you can say that this is the level 0 devices. So these are the several IO devices, input output devices, the control valves and some sensing devices. Like here you see this is the picture of a flow control flow sensor, which is known as Coriolis mass flow meter. Okay, so depending on the different control loop, different sensors will be present, and the information sensed by this sensor are given to the controllers. Okay, these are the controllers. Next level, the controllers are sitting through the IO communication bus. Okay, and here you are observing that these devices are connected to the controller through a bus. Fine. Now you are observing that, so this controllers can be a computers. Now you are observing that several consoles are there. Okay, several computers you can observe, which is written as a workstation. Okay, which is written as a workstation. So the uses of this computer will be different if they are sitting at the different level. Okay, so that's why modern control systems are well suited for hierarchical control, because level 1 controls, which consist of devices with direct connection to the process, can be cascaded to the supervisory and management levels of control. So these computers which are connected with these controllers can be act as a supervisory control controller, or they can be used as a management levels of control. So that's why we are interested to know that what are the hierarchy present in terms of control, such that we can understand that what are the uses of computer at different level. So so now we are going to discuss that there are basically 4 levels in the hierarchy. What? The first level, you see, the all direct connections to the process are uniformly referred to as level 1. These basic controls includes all sensors, final control element, continuous PID control, sequential interlocks, alarms, and monitoring devices. In some systems where several levels of basic control exist, they are referred to as level 1A and 1B. Okay, and so level 1, the uses of computer will be the will be the final will be the basic controls. Okay, and then level 2 supervisory control is universally called the level 2. So in level 2, the supervisory control will be the control function of these levels are targeted to increase production, improved environmental protection, energy conservation, optimization, predictive maintenance, and plant wide safety. So these are the work of a supervisory control, and this work has to be done by a set of computers which may be sitting at the level 2. Okay, so in level 1, basic control actions, which is directly going to interact with the process through the IO devices like sensors and actuators, and level 2 will be the supervisory control. Now we are moving to the level 3. In some plants, the area controls or inter area coordination is called level 3, while in other plants it is included in level 2. Okay, in some plants the management functions are referred to as level 3, while in the others the scheduling and management information functions are called level 4. Often the level is split into level 4A and 4B, where 4A covers contact with the plants, that is scheduling, etc., and 4B covers contact with the upper management. Okay, and what are the managerial functions are to be executed in level 4? The management functions include marketing, financing, human resource, production scheduling, and inventory tasks. Some generalized software packages already exist for enterprise resource planning, that is called ERP, and material requirement planning, that MRP. So this ERP, MRP, all these things should be done by a set of computers. So that's why it is required to know that what are the control hierarchy present in the plant. So it is divided in four level: level 1, level 2, level 3, and level 4, and we have understood what are the work must be performed by a set of computer which are sitting at the level 1, level 2, level 3 and level 4. Okay, so now we will see that how the uses of computer has evolved from the past days to this modern industrial application in terms of this hierarchical control. Prior to the introduction of the use of computers for industrial control application, the standard industrial control system consisted of a large number of single loop analog controllers, either pneumatic or electronic, as diagrammed in the figure. So here you can see that initially the uses of computers in the process control was not there. Mainly the analog controllers, means all the PID actions were generated by operational amplifiers. They are implemented with the operational amplifier. So there was no use of computers initially. All the control task was executed by the analog controllers. Note that in the figure, the level 1A refers to those instruments that have no signal readouts, that are readily available to the operator. Some field mounted controllers, means the instrument which is used in the level 1A, they do not have any capability to transmit the signal. Okay, means here you can see that those instruments that have no signal readouts and that are readily available to the here 1A refers to those instruments that have no signal readouts, means here you can see that for the operator no signal readouts are there. The signal is transmitted, whatever the measured value by the process is transmitted to the analog controllers. Okay, there should be no readouts. And in level 1B, devices have transmitters and provide indication to the operator by a pointer or a strip chart, etc. These later devices include the standard PID, that is proportional, integral and derivative control mode of controllers. Okay, so initially there was no use of controllers as a use of computers as a controllers. The analog controllers were there. How the controller is implemented? Using operational amplifier. All this P action, integral action as well as the derivative by action is performed by the operational amplifiers. Okay, and if you go for the more old days, you will find that at that time the controllers are generally implemented by pneumatic devices. Okay, the output generally was in air signal and the range of the air signal was 3 to 15 psi. Okay, so and then the analog controllers has come. Now at the initially the introduction of the computer in the process control industry was not in the form of controller. They basically used for the data acquisition or as a data loggers. The computers were first used in industrial plants not as controllers but as monitors, data loggers and data acquisition. So there was a process. The introduction of the computers generally used to monitor the process or to log the data or to do the data acquisition. Okay, so the early computers served only for the data collection and monitoring. So now here I want to clear that what do you mean by the data acquisition and the data loggers. Okay, so this basic idea must be clear. The data acquisition is the process of measuring an electrical or physical phenomena such as voltage, current, temperature, pressure or sound with a computer. A DAC system or data acquisition system consists of sensor. You see here one block diagram has been shown. Sensor, then DAC measurement hardware, some DAC measurement hardware which may consist of signal conditioning unit along with a analog to digital converter. Okay, and a computer with programmable software where the driver software will be there or as well as the application software will be there. Compared to traditional measurement system, PC-based DAC system exploit the processing power, productivity, display and connectivity capabilities of industry standard computers, providing a more powerful, flexible and cost-effective measurement solution. In contrast to that, if you understand what do you mean by the data loggers, the data loggers is the measuring and recording of physical or electrical parameters over a period of time. Okay, so they do not have any signal processing capability. So what is the use of data loggers? Now data loggers are used in a variety of applications, such as in vehicle data logging, environmental monitoring, structural health monitoring and machine condition monitoring. Common measurements include temperature, strain, voltage, current, pressure and acceleration. So there must be a sensor and some data logging hardware will be there, which will use to interface with the computer, and you will store the whatever the measure you will measure as well as record. Okay, so now we will continue to discuss about the use of computers in process control industry. So again I am repeating, as initially there was no use of computers in the process control industry. There was analog controllers which is implemented by operation amplifier. Later on the computer is introduced not as a controller, it is introduced as a monitoring, data acquisition and data logging devices. Okay, as a devices. Now these installations were quickly followed by the first supervisory controllers early 1960, which is use the computers to change the set points of the analog controllers. So next use of computer in the process control industry is not as a controller. Next is supervisory control level computers. What is the use of supervisory level of computers? Now they are used to change the set point of the analog controllers. Means see, still the analog controllers were present. Okay, so this is the level 1A, where the specialized controllers are going to interact with the process directly, and the measurement which is done by the sensor in a sensor which is going to the analog controllers, and there must be some display. So that is level B. And to change the set point of the analog controllers, we are going to use the supervisory control level computers, and there must be a supervisor console. What is the use of supervisor console? Supervisor console is used to change the set point of the analog computer. So that is you see the use of computers in a level 2. Okay, as a level 2 we are finding. So now the level 2 supervisory computer is used to adjust the set point at the level 1. So now next we are going to discuss that next evolution of the use of computer in the process control industry. It was the desire of most control engineers who were working with early computer control system to completely bypass the analog controllers and have the computer directly control the valves or the actuators. This resulted in direct digital control. So this architecture what we are going to discuss, where the first actually the computer is used as a controller. So now we will discuss what do you mean by the direct digital control. Okay, the architecture of direct digital control. Here you see one block diagram has been shown. So we have a process. So now suppose this is a orifice where the DP transmitter, means differential pressure transmitter, is there, which is going to measure the differential pressure created by the orifice. So this measurement data is going to the common equipment through the input multiplexer, because there are so many process variables will be there. So you have to collect all the process variables from the field, and which is coming to the common equipment through a input multiplexers. Okay, so now this measured value is going to the analog to digital converter, and now the digital form of this data or measurement data is going to digital computer. So now when it is going to digital computer, this digital computer is acting as a controller. Now based on this data and the algorithm what it is written inside the computer, it is going to calculate the control action. So now this control action is going through the output control to the output multiplexer, and now ultimately it is going to control this control signal is going to the final control element to actuate or to control the manipulated variable such that the control objective is fulfilled. Now to interact with this digital computer or this controller, several console will be there. Why these consoles are required? These consoles are required because through this console any supervisor or the operator can interact with the digital computer. So now this is the architecture of direct digital control system. So this architecture having several disadvantages. What are the disadvantages? The disadvantages are that although these computers had much greater speed and memory size compared to earlier system, their use lead to still further problems. What are the problems? First problem is that the vast amount of wiring and communication system required to bring the plant signals to the centralized computer location. You try to understand, in a plant thousands of or more than thousands the process variables will be there. So that all the process variable are required to be measured, and you have to send them to a central computing facility. So you require a large amount of wiring which will come to a central computer room, and which require the wiring, a vast amount of wiring and communication system. Okay, and due to that what can happen now, and similarly the return the control signal to the field was a very expensive. Okay, so you have to return this return the control signal to the field also. So this whole wiring signal and the communication system is definitely a very expensive system. Not only very expensive, and unless it was very carefully designed and installed, it was prone to electrical noise problem, because so many wires are also, so many cabling will be done. So one cable will be adjacent to the another cable. So then what will happen? The electromagnetic interference will be there. So it was prone to electrical noise problem. So because all of the, and another problem is what now, because all of the control functions were located in one computer. So we are sending all the information to a single computing facility, and that is acting as a controller, and it is going to decide based on the measurement signal and the control algorithm, then it is producing the control signal. So because all of the control functions were located in one computer, the possibility that the computer might fail resulted in demands for a complete analog backup system. So if the central computer fails, then what will happen? The entire process will be shut down. So then to resolve this issue, you require a complete analog backup system. Means if a digital control system fails, then you can switch to the analog control backup system. It greatly increases the cost. As a result of these difficulties, management in many companies reacted disapprovingly the computer control, and there was a hiatus in computer system installations until the 1970s. Okay, so this is the phenomena, or this is the incident I'm telling during 1960s. Okay, so where the computer is used as a centralized control system, which is known as direct digital control system. Here one thing I want to mention, that how this digital computer is acting as a controller. If you think for a single loop, okay, here several loops are there. If we will focus in a single loop, how it is working, you see, in any digital control system, the sampled signal, the analog signal, what it is measured from the field must be sampled. Okay, and then it is fed to the comparator. Now you have a process value. That process value is measured by the measuring element, that also has to be sampled in the same rate, and it has to be given to the comparator. Now comparator is producing the sampled actuating signal or the error signal which is given to the digital controller. Now digital controller, based on this sampled error signal, will produce the control action which is obviously in digital in nature. Now you know that all the final control elements are analog in nature, means the control valve or other than the control valve, any final control element like the DC motor, okay, they are continuous in nature. So that's why what you require, the control signal what it is produced by the digital controller are to be converted in the analog form by digital to analog controller converter, which is known as a hold device also. Okay, so this hold device or digital to analog converter is going to convert this control signal, digital control signal, to the analog one, and this analog control signal is executed through the final control element such that the manipulated variable of the process control of the process can be manipulated to achieve the desired output. Okay, so this is the work of any digital control system which must be used in a as a single loop in a direct digital control system. So now we have understood that this direct digital control system having several disadvantages. First disadvantage already we have discussed, that vast amount of wiring and communication system, and second is that centralized and computing facility. So if the central computer fails, then you require a complete backup system, analog backup system. So this is the architecture has been shown. You see here the direct digital control and here the supervisory control level. Okay, so the complete secondary digital control, supervisory plus direct digital control with associated analog control backup. So here you see the analog backup devices is there. If this direct digital control fails, then what will happen? These analog backup devices are going to act. But here in terms of level control hierarchy, if you see the level 1, you are finding that direct digital control is executed by a set of computer, and in the supervisory level the computer is used which is in the level 2, which is generally used to change the set point of the direct digital controller. Okay, so now this is the scenario during 1960, I'm telling, and from the 1960 people are searching the alternative. What could be the alternative for this situation? So because of this problem experienced with the centralized computer system of the late 1960, most of the new computer projects of the early 1970s were relatively small, specialized project that took advantage of the capabilities of the newly arrived micro or mini computer. Okay, however at this time two other developments were underway that would forever change the digital computer based control and indeed all process control, because there at that time two very important development has occurred. What are they? The first, the first of these was the rapid development of the integrated circuit IC and the resulting production of the all important microprocessor and microcomputer. So now the introduction of microcomputer or microprocessor has come. Okay, and second development was the courageous effort begun by the Honeywell company in 1969 to design an alternative to the unwidely and unreliable centralized computer control system, that is direct digital control system. This alternative was the distributed computer system. They have introduced this revolutionary idea about the distributed computer system in comparison to the centralized computer control system. So now we are going to understand what the features of these distributed computer systems are. Okay, so this distributed computer system also known as in generalized way supervisory control. So what are the tasks of a supervisory control? Now typical tasks performed by the supervisory controllers are the set point computation and setting of different control loops, performance monitoring or diagnostics, startup, shutdown, emergency operations, control reconfigurations, tuning, operator interface, graphical interfaces for supervisory operation, manual supervision and intervention. So these are the main features or main tasks must be performed by any supervisory control action or supervisory controller. So now we want to understand that what is the meaning of this distributed control system. You see there are three terms are there, distinctive three terms are there. Distributed control system. So we want to understand what do you mean by the distributed. Okay, so distribute its functions. So as its name implies, the DCS has three essential qualities. First is the distribute its functions into relatively small set of semi-autonomous subsystems which are interconnected via high-speed communication network. So first thing you have to understand that why it is called distributed, because it is distributed by its function. Previously what we have observed that for the direct digital control system, a single computer, a central computing systems were there, so everything has to be done by the central computing facility. But here we are finding that in DCS the functions are distributed. So what are the functions? Now, data collection, process control, presentation of information, process analysis and supervision, storage and retrieval of archived information, the presentation and reporting of information. So these are the main function of distributed control system, which is distributed by semi-autonomous subsystem. So what will happen if this modular concept is introduced? So if a single modular, suppose in this in between all these functions performed by a individual semi-autonomous subsystem, suppose data collection, if a subsystem is not working, then all other subsystems will be not affected by the by the not working of this data collection system. So that's why this facility we are going to get when the functions of DCS are distributed. So what are the advantages of distribution? Now the distribution of the functions has several advantages over more classical process computer architecture, including lower exposure to component or subsystem failure that just now I have discussed, and better isolation to facilitate maintenance and upgrade. Means suppose for the maintenance some of the parts has to be repaired, so what will happen, the whole performance of the systems are not going to be affected, only part of the process you can do the maintenance. For that it is not required to suspend all the processes. Okay, and upgradation also, if you want to upgrade it, then partially you can upgrade, or subsystem wise also you can upgrade. It is not like that for the upgradation the entire process has to be suspended. So better partitioning of application requirements for the different process areas. Okay, so different process may have different requirement. So if you have the subsystem, you can design that subsystem according to the different requirement by the different process areas. Improved modularity for application development. So modular wise it is, so every modular having different applications, so you can do the application development in a modular wise. Then next is the facilitation of geographical distribution, which reduces installation cost, reduced wears, and provides more localized operational supervision while offering global access to information and control capabilities. So this is a very important feature, because you see that it is also geographically distributed. Definitely when the functions are distributed, then then it is distributed by geographically also. So then what will happen, every information is not required to come from the field to the control room, means then you can save the wiring also. So what will happen, from the field, suppose some module will be there near to field, from field sensor the information is going there. Okay, so now what will happen, you in this way you can reduce the and wearing. And also it is not like that if due to that you are losing the supervision of whole system. It is not like that. Ultimately what will happen, though you are localized by operation, but all the operations will be supervised globally. Okay, so that facility also you will get by the distribution. Then second is the automate the manufacturing process. So this is another important feature offered by the DCS. The second is to automate the manufacturing process by integrating advanced regulatory control, logic and sequential control, and procedural languages into a cohesive application that is integrated with a variety of advanced application packages ranging from batch to expert system. So here with the advanced control technology which is integrated with the DCS, by which you can achieve the automation. The control aspect of the modern DCS has expanded to include information that is capable of supporting such manufacturing enterprise application as activity-based cost accounting, production scheduling and dispatching, preventive or predictive maintenance scheduling, then validation of employee job certification and readiness, and then information exchange with business, logistics and transportation applications. Okay, and last is the integrated system. So you see DCS, distributed control system. So we have understood about the distribution, we have understood what are the control facilities are incorporated in DCS to achieve the automation, and last thing is the system. So you can view DCS as a system. And what is the meaning of a system? A system as a set of arrangement of things so related or connected so as to form a unity or organized as a whole. Okay, so how it is integrating the system? The system aspect of DCS organizes the command structure and information flow among its constituent parts so as to have it act as a single automation system unifying the various subsystems. So though it is functionally distributed or geographically distributed, but it is unified or integrated as a system. Okay, so how it is now, it is DCS organizes the command structure and information flow in such a way that it is integrated as well as united. How? Now the process signal input and conditioning. Okay, so this this has to be performed by a subsystem, but it is unified way. Okay, so that's why it is told it is told that that the system aspect of a DCS organizes the command structure and information flow among its constituent parts so as to have it act as a single automation system unifying the various subsystems including process signal input conditioning, process actuator input signal output, regulatory combinational and sequential logic, and procedural and supervisory control, human readable process displays of current values, alarms, trains and calculation, human actions including set point changes, manual overrides and alarm handling, application subsystems, and information storage subsystem, communication subsystem. So these all subsystems will be integrated in a DCS. So now I think this is sufficient to understand that how the evolution of DCS has come in terms of uses of computer. Now next class we want to understand how really the evolution of DCS has occurred. Okay, and also in details we are going to understand what are the architecture of DCS is.